All right, we are up to 25 people already, so I will start by just welcoming everyone back. Hope you all had a good new year. And for anyone that is new or attending this call for the first time, we hold this industry-wide call every month for any company that is or desires to participate in the cultivated meat value chain. And the purpose of these calls is really to introduce and welcome new solution providers into the industry, with the end goal of establishing new collaborations that are going to accelerate R&D and commercialization. So if your group is interested in presenting on a future call, or if you're working with a company that may benefit from being on these calls, please do feel free to put them in touch with me directly. So a few housekeeping items before we begin. I wanted to share that we recently launched a new analysis that is focused on growth factors, which examines questions such as what quantities of growth factors will be needed for cultivated meat, what are suitable production cost targets, and how will these inputs be regulated. So I'll drop the link to that in the chat, but just wanted to thank ahead of time some of the companies that worked with me on this report to get it out. So thank you for that. We also have a few events coming up, including a seminar about bringing cultivated meat to market in the United States, as well as a networking event for the cultivated meat community. I'll also drop those links in the chat in a moment, and we'll share those links in the follow-up email as well. And then lastly, I just wanted to give a heads up for you to please keep your eyes out for an email at some point in February about another survey that we're going to be conducting that's focused on bioprocessing, scale up, and facilities for the industry. Basically, we really want any company that has a facility or is planning one to be able to respond to this. And your participation in it is really crucial to us getting a good data set. So please help us help you out by ensuring that that email gets read and the survey is eventually completed. So you'll see more details about that later in February. So for today's speakers, I'm pleased to welcome James Kendall and Urian Gillison from TTP, who will be talking about the importance of computational tools in overcoming scale-up challenges. And then about 1:30, we'll turn it over to Josh Bachner from Moliere, who is going to discuss how their nanobubble technology may be able to improve oxygenation in your processes. So over to you, James.
All right, thank you for the welcome, Elliot. And thank you everyone for joining. We're really looking forward to presenting this talk today on what we believe to be the importance of in silico bioprocessing. So with this, we explore TTP's vision on how computational tools fed with suitable experimental data can allow for more successful scale up within the future food market, specifically for this audience, but also the broader industrial biomanufacturing market. As a couple of introductions, my name's James Kendall. I'm a consultant within our deep tech industrial technologies team here at TTP. My own background's in material science and manufacturing, and I'm carrying forwards the technology engagement with this new growing industrial bioprocessing market within TTP. My colleague Urian, who you'll hear from later, is an applied mathematician. He spent many years in academia in very complex computational fluid dynamics, and he's working with us on this campaign, an engagement with this market with modeling tools that we'll explore later on. I'll let him give a quick introduction once we get to his section of the presentation. So to quickly introduce TTP and understand the approach and the angle that we're coming from for these technologies, we're a product and technology development company who aim to help our clients to bring their inventive concepts from discovery through to deployment in the market, with a key focus always being on commercialization. And this is a really important factor that we consider in parallel with the fundamental technology and making the science work behind the engineering. And how we do that, the sorts of activities that we do day to day, we span really early opportunity discovery and prototyping. Much of the future food market is potentially at this stage. And we apply science to drive both really rapid and guided research and development cycles, but also the techniques that are fundamental to the engineering, the real world deployment. The science is fundamental to making those work. We take that science all the way through to prototyping and detailed engineering of the systems that we design, and eventually through to scale out, to transfer to manufacture, both with our manufacturing networks, but also those of our clients. And we work at any and all of these stages of this development cycle. And we have over 30 years track record of about 350 scientists and engineers across all disciplines to enable this sort of phase development across clients ranging from life sciences through to advanced manufacturing, through to satellite and space, and many other markets in between. So I think all of these skills have been thoroughly put to the test over the years in the bioprocessing space. So TTP is not new for this, and this is why we're trying to bring some of the insights that we've gained from those markets to this new market that has very similar technology fundamentals, but very different commercial drivers. And we're seeing that there are some very interesting overlaps, but some very interesting contrasts as to what we think will enable scaling in this industry. And that goes back a couple of decades to TAP Biosystems. So this is a company that was spun out from TTP before the turn of the millennium. And that was eventually what produced the Amber 250, acquired by Sartorius and commonly used today in many biolabs in this industrial bioprocessing space. Through to more recent engagements within the life sciences space and cell and gene therapy, where there are very similar drivers to try and bring costs down and have very high sterility for cell culturing. But of course, a very different cost point to foods that we'll be exploring in this webinar. So as mentioned, I think that the way we're driving we're addressing some of these drivers for scaling of really innovative techniques is at this overlap of life sciences, so all the biochemistry, but also the industrial technology that enables that scale up, coming from the deep technology side of the business. So where does the computational side fit into all of this? Well, we believe that current methods borrowed from biopharma can't achieve cost-effective design and deployment of these new technologies. This is a topic that we've chosen to focus on in particular because it faces all players in the ecosystem, from formulation developers through to equipment developers. And we believe computational tools are a key part of the answer, as it allows more informed optimization with reduced experimental intensity. This is something that we've recently published a white paper on. It's available for download online and will be hopefully distributed after this webinar. So today's sort of a flavor of the sorts of points we've been exploring as to where we think it can be implemented in detail. And we'll hopefully be able to address some of the high level arguments that we put forward in the white paper. So what is the challenge? Why do we think that current tools are unsuitable? We've identified that there's very high cross-discipline, multi-dimensional dependency between the biochemistry that's happening at the R&D level and the bioreactor design that has to happen at the industrial scale for manufacturing at scale to be feasible. And we're seeing that the current approach is often to develop the biochemistry first for reasons that are very, very understandable and very reasonable, in that it's completely infeasible to be doing trials at hundreds or thousands of liters. So doing the biochemistry first is the resource efficient way to do it. However, all of these interdependencies end up with unexpected behavior once we start to change the process conditions under which that biochemistry is happening. This often results in going back a step to try and review the biochemistry, potentially choosing an unsuitable strain to start with, and the reactor design also itself being a very resource-intensive R&D cycle to try and bring new bioreactors into the market. And fundamentally, we're saying that we can't take this sequential optimization approach anymore. There's been many examples where people take 2 steps forwards, gaining very good process insight with manageable resources and parameter control into the biochemistry, but then 1 step back with this unpredictable behavior once the length scales and the shear rates and so on, the sorts of things that Yuri and later will explore, vary very significantly from well plates through to small bioreactor through to large bioreactor. And this scaling iteration means long development cycles. It means increased cost and time, both of which hinder likelihood of some commercial success, which ultimately we need a viable resulting process at the end of this, one that is at a good cost point for consumer acceptance, with sufficient margin and quality control to be both commercially and safely viable. But it also needs to account for the R&D effort required to get there. How long are investors willing to stay with this technology? How much money are they willing to put in to get to that viable resulting process at the end? So we suggest, rather than this sequential approach, which is very resource intensive, where we start with the biochemistry first and then try and shoehorn that biochemical optimization into available bioreactor designs, which can ultimately lead to risks of carrying forward fundamentally unsuitable designs at scale. What if we take a parallel approach, where modeling is a very key part of this for reasons we'll shortly explore, but essentially it's parallel physical experimentation, because we understand that biochemistry is far too complex to model from first principles, and therefore does certainly require some physical experimentation, but augmenting them with computational in silico experiments. And being able to iterate both of these loops in parallel means that we're more likely to find a biochemical design that is scalable. We're more likely to find the conditions under which that biochemical strain performs the best. And we're able to have more confidence with lab scale resources to move towards those very large scale resource intensive scale up challenges in design and pilot lines and so on. With the outcome being hopefully better optimizations, better processes at the end of this cycle, hopefully in less time and hopefully with fewer physical resources to get to that end result. So very specifically where computational tools are critical here. It's not just actually in the design stage. We think that the effort put into the design stage can be carried all the way through to eventual deployment. We have to understand that we can't reinvent the wheel immediately. So we'll probably be starting with available equipment, large stir tank bioreactors, for example. We need to understand what the conditions are in that available equipment as our starting point. And critically, we need to be able to replicate those conditions. So I mentioned that the biochemistry is far too complex to model from first principles. We need to somehow replicate these very complex conditions in a lab scale environment in which we can put the cells to understand their behavior at those conditions. We can then feed that back into our simulation, so add in an extra level of biochemical activity on top of purely the complex fluid dynamics. And then depending on where you're coming from, if you're a biochemical food product formulation developer, perhaps it's iterating the biochemistry. So taking the results of that simulation, modifying the cell design to be more resilient to a specific aspect or a specific stressor in the system, gain some more data to see which of your new family of iterated strains performs the best, and feed that back into your simulation to see whether that's had a significant enough impact at the large scale to overcome some of the yield issues that we're often seeing. If you're a bioreactor designer, perhaps it's a case of taking your the common cell designs that are out there in the literature and in early startups, and starting to bring onto the market better equipment that provides a more nurturing environment for those cells to try and produce as much product, whether that's biomass or whether that's precision fermented other product. Try and give them a condition in which those cells have the best chance of thriving and producing maximum product. And then eventually through to deployment. I mentioned all is not just lost in the R&D. These very complex models which have been built up over many iterations could and should be implemented as, I hate to use the buzzword digital twins, but models that can be that can infer the process from what will have to be relatively limited analytical capabilities. If we're to try and implement cost-sensitive analytical technologies, we have to accept the data will not be a complete data set as you might get in a well plate, for example. There'll be very high spatial variations. There'll be potentially very large variations in time as well, and a lot of noise that is perhaps unpredictable. So how do we take that input data and have a good idea of what's going on inside the process in order to control it in real time? So this is our blue sky vision as to clearly there's a need for computational tools. So the main question is why are they not being deployed at the moment? And we see two key challenges. The first one being that commercial modeling packages do not have sufficient functionality. The multi-physics nature of these problems is far too complex for them to handle. And the second one is the need for representative experimental data to validate those models. And unless you validated your models at a large scale, especially, the model has very little value in trying to increase the confidence you have in the predictions it's being made. So we see also this replication of those large scale conditions with lab scale resources as being another really large bottleneck to try and deploy this sort of approach. So with that, I will hand over to my colleague Jurian, who will explore some more specifics of the computational techniques and the key parameters that we think need further exploration and deployment to enable this vision that we see of parallel R&D and development from design to deployment.
Yeah, thank you very much, James. Yeah, so that was a kind of a high-level overview of our vision. You know, like how do we deploy computational tools in the bioprocessing industry, especially when it comes to scaling up. And in the last couple of slides, we would like to basically show a couple of examples, because we are talking CFD, so we should at least show a couple of colorful pictures. So that's what we're going to do next. We're going to show a couple of colorful pictures and talking about the role of computational tools in scaling up. And we also will show an example where we actually have made a device using computational tools. So yeah, maybe next slide. Oh, that's one too far. Maybe one back. Yeah. Right. So yeah. So the idea really is to use this capability of computational power, and what we do, particularly at TTP, specifically what I've been doing at TTP is develop in-house software that is able to get very detailed, right? So we are able to go in a very high resolution simulations. For instance, here you see very high resolution simulation of a stirred tank reactor, and the grayscale that you're looking at is the hydrodynamic stress in the system, which looks very detailed and convoluted. That's of course because it's a highly turbulent flow, and we are really studying in this case the fine structure of this shear stress. And why do we look specifically at shear stress? Because we are dealing with meat. We want to produce meat from cells, specifically mammalian cells, and these one of the main problems when you try to do this at large scale is that typically stresses can be quite detrimental at large scale. Typically, you have to rotate faster at large scale than at small scale in order to get an efficient mixing. So you get extremely high shear stresses that can be detrimental for cells. So yeah, that's one thing that you need to kind of bear in mind when you are scaling a process up from lab bench to megaliter scale. That's okay. How are the shear stresses going to change? And can I somehow predict those? So that's one aspect, and another important thing when you think about stress and force on cells is the effect of gas bubbles. gas bubbles, when they rise in the tank and they hit the free surface at the top, the bubble bursts, and this will create some sort of pressure shock whenever the bubble bursts at the surface. And these pressure shocks, they can be also very severe. So I will talk in a few slides also a little bit about these pressure shocks induced by bubbles. But yeah, so maybe we could go to the next. Yeah, so want to talk also, in addition to the mechanical stress, we also have to consider, let's say, the chemical stress. And for that example, I consider here the distribution of oxygen, right? Thinking about the distribution of oxygen, or you can also think about distribution of nutrients, but some distribution or toxic. But let's say in this example, we simulate a stirred tank with an oxygen source, where these circles in the movie, each circle is a gas bubble. And the color that you see in the background is the dissolved oxygen concentration. Blue meaning low level and orange meaning high level. And interestingly, if you have a stirred tank reactor and you scale it up, right? And you say to yourself, oh, I have to be careful. I should not change the shear stress. So I scale it up in a way that I keep the shear stress fixed, which roughly means that you keep the impeller speed fixed. Then, however, the oxygen variations are not going to be fixed. So you can keep, let's say, the shear stress fixed, but then the chemical stress, which is kind of the word I use for oxygen variations, because those can also be detrimental variations, gradients. Those then will not be fixed. So in the image, the three images on the left, on the bottom, you see oxygen variations at different scale while keeping the shear stress fixed. So on the left, it's a 1 liter reactor. And in the middle, it's a 1 cubic meter reactor. And on the right, it's a cubic 10 meter reactor. So that's 1 million liters. So going from left to right, we go from 1 to 1 million liters. And we study oxygen variation. And we plot the oxygen variation in the graph as a function of time, where the variation is, we call it heterogeneity. And you see that go from blue to red to yellow, the heterogeneity increases with scale. Well, it increases, it doesn't increase very, it doesn't increase with a high power, but it definitely increases with a certain power. So understanding these scaling behaviors is, of course, essential if you want to design your bioreactor at scale, right? If you know on forehand how different things scale, then you know if this process is going to be working, yes or no. So that's already kind of a first pass design that you can make. Yeah, so lastly, I would like to talk a little bit about, again, going back to the gas bubbles, the gas bubble, the forces that are induced by gas bubbles when they pop the surface. Again, these gas bubbles in a large bioreactor will be typically much larger than in a small bioreactor, right? So you have maybe millimeter in a 1 liter reactor, but you might have bubbles of 10 centimeters in a 10 meter bioreactor, because all that gas is coalescing and creating big pockets of gas. So of course, all the conditions are extremely different. And now the idea is, okay, how do we now actually know how the cells are going to respond to these big weird conditions in the large scale? Right? How do we know how it's going to respond? So one way to say is, let's do an experiment at 1 million liter scale, but that's a bit costly. So what we say is, let's use all this insight and scale the things down. So if we understand the cavitation pressure of a gas bubble that pops the surface in a large scale reactor, then we say, okay, let's mimic that pressure at small scale. Of course, we can't make a big bubble in a small scale, but we can make a very high energetic bubble using inkjet technology in a microfluidic chip. And that's exactly what we show here. This is a product developed at TTP. It's not designed to mimic a large-scale bioreactor, but this is a cell sorter for medical applications. And you can see the microscope image where you have a channel, and then there is something happening, and then the cells go either up or down in that channel, right? That's what you see in the image. And the middle one is the computational model, where we simulate the interaction of a cavitation bubble that we generate using inkjet technology, and really dig down on the relation between cavitation pressure and cell trajectory. And by doing these detailed simulations, we were able to kind of design this cell sorter, and then this thing can sort at a frequency of 10 kilohertz. And every let's say, what is it, 100 microseconds, there's a cavitation bubble popping that pushes the cell exactly in the right amount in order to be sorted. So I think that's the end of our time. The main takeaway is that our vision is to accelerate scale up by scaling down conditions. So understanding the conditions at large scale and then creating these, recreating these conditions in small scale experiments, and then see what happens to your cells. I think that's the way forward. But that is one way forward to realize future food ambitions. So again, thank you, Renee and Elliot, for the time and for your kind collaboration. And also one more shout out for the white paper. We will be posting the link when this video gets posted. So hope everybody enjoyed it, and we look forward to questions. Thank you very much.